Hi, my name is Liise Vihmann. I am an early stage researcher here at TalTech, and today I will tell you a little bit about the performance and assessment of bond lines of engineered wood in fire. My supervisors are Professor Underused and Professor Martina Skiamenta. To begin with, I think we all know that building with timber is becoming more and more popular. And to be able to build taller and bigger timber buildings, we also need larger cross-sections and longer lengths of elements. So we use engineered wood products for that. And to move forward, engineered wood products consist of two materials, timber and adhesives. And there are a lot of adhesives being used in production today. The most popular families are shown on the slide, but I would like to elaborate that the phenol-resorcinol-formaldehyde adhesives, also known as PRFs, are the oldest ones. So they have been around for around 100 years or so. And they are known for their very good stability at ambient temperatures and also higher temperatures. So those have been used mostly for a long, long time. But when cross-laminated timber entered the market a few decades ago, we also needed to cover a lot more area with the adhesives. And so since the PRFs are quite expensive, new adhesives entered the market. What happened is that when scientists started testing these adhesives in higher temperatures, it turned out that not all adhesives perform the same at higher temperatures. So largely it has been known that adhesives can be grouped into two groups. So the first group contains adhesives for which the bond line integrity is maintained. That means that throughout the fire, the charring rate remains constant. When timber burns, a char layer forms, and this char layer performs as a protective layer, sort of. And the timber behind it is protected from high heats. This is true for the PRF adhesives. But what was discovered during testing was that for some of these adhesives, the bond line integrity is not maintained. So that means that when the char layer forms and it reaches the adhesive bond line, the adhesive softens, loses its strength, and the char layer falls off, which means that the timber behind the char layer is completely exposed to fire now. So it starts burning faster, or charring faster. And this is taken into account in the new Eurocode with a second charring model, the step model. Now all that remained was that we had to make sure how do we group or divide the other adhesives? How do we know which adhesive performs in which way? So for that we need a classification system, or many of them, and also to make up the systems we need testing methods. So I will give a brief overview about the testing methods that are used currently for evaluating the bond line integrity. So the first test method is maybe the most grandiose method. It's the full-scale fire test that's mainly used in North America right now. And essentially it's just that the building is built up, the whole structure is built, it's burned down, and it's just checked whether the structure held up long enough with that specific adhesive in those specific conditions. And since it's very expensive, I would say it can go up to 6 figures, and also a resource-intensive method, mostly only one test is conducted. Also, even if we had the means to repeat the test, it would be not under the exact same conditions. So one test might not be enough for a scientific method, in my opinion. So in Europe, we have stepped down a little bit, and we have implemented the glyph method, which is a model scale method, where we burn 2 specimens, a test specimen, a reference specimen, at the same time in a model scale furnace. And after the test, we just compared the charring depths, and depending on the difference between the reference specimen and the test specimen, we can divide the adhesives. Also still pretty expensive, I would say. One test can go up to 5 figures. It's also time consuming, needs a lot of materials, but we do have more test results from these tests compared to the large-scale tests. The results are more conservative compared to the full-scale tests, which is not actually a bad thing, because we can apply the results more widely. And then we have been developing here and in Europe in general small-scale test methods for evaluating the bond line integrity. And the first two of the three have been developed here at TalTech. And the first one is a small-scale cone heater test with shear strength assessment. So we take a specimen about this size, heat it until the temperatures in the pond line reach what we want. Typically it's 290 degrees. And after the temperature is reached, we load it in shear until failure, and we can just compare the shear strengths. We can do many tests in little time with little resources, and there are only a few external factors that influence the results. The results are, however, conservative, which means that we can also apply it very widely. The second method, also developed here at TalTech, is the small-scale cone heater tensile test for finger-jointed elements. So we take a finger-jointed element like this, we put it under static load, heat it, burn it from the top until failure happens, and we measure the time to failure. Also, we look at the failure mode. So still, many tests with minimal time, minimal resource, few external factors, and very conservative results. There's also a third test method that has been developed in Germany by our colleagues, which are the tests at elevated temperatures. So specimens are heated in an oven up to the desired temperature, and then it's tested in shear to evaluate the joint strength. Also, we can do many tests, minimal time, minimal resources. But I would say that the positive and the negative side of this is that there's no direct influence of fire or charring. So we have plenty of test methods. Now the question is, how do we decide what the classification systems will be? Where do we draw the line between linear model and step model? So right now the new Eurocode 5 will use the model scale test, the glyph test in furnace, to assess the bond line integrity for face bonds, so say cross-laminated timber, glulam beams, and so on. And I'm very happy to say that the second method included in the Eurocode 5 is the finger joint method. So this method, small method, and it is used for finger joints. Hopefully, maybe in the future, we can also replace the furnace test with something smaller, and we're working towards that. Another part of my research has been to compare fire tests and elevated temperature tests to see if we can maybe completely go away from the fire tests and just look at the elevated temperature tests and draw our conclusions there. And the results have been that I would say we can use the elevated temperature tests to evaluate the bond line, but it's way more conservative, I would say, and also it underestimates some of the adhesives greatly. So for these adhesives, we would have to still use maybe fire tests. So for innovation and future, I would say that we still have research to do. For example, all of these test methods are mainly used for spruce, and we would like to extend these test methods to different wood species. It is also important to keep updating and refine the standards as we find or learn new information, not just after every 20 years. Also, we need to raise awareness of fire safety. And the biggest goal or dream is to be able to model the adhesive joint behavior in fire, so we wouldn't maybe have to do tests at all in the future. Thank you.